Hey, it's time for week 5 of Chemistry 1100C. I'm Dr. B, and here is the summary slide. Here's the items that we'll be covering. I think it's fair to say that this is the rest of the course, really. This is a wide variety of topics, and here are the formal assignments here. These have no point value, but these are the things you need to learn in order to do the things that have point value, which are shown here. We've got 3 labs, a quiz, and an assignment. Here is the suggested pacing. Take a couple days to master the foundational material. Start with the labs, perhaps around Wednesday or so. Complete them if you can by Thursday. Work on the assignment towards the end of the week. Get that quiz done by, say, Saturday. And if you do that, you can rest on Sunday. Here's how the points break down. It's 184 points total. Not sure if you can see all of that. But my advice would be to do your best to get high scores on the labs. Sometimes these materials can be handed in multiple times. You can retry things. The assignment, talk to each other, make sure you're getting them right. You all get the same questions, so learn from each other. Email me if you have issues, but take your time with those. Try to get those right. The quiz is automatically scored, and do your best on that. Everything I have to say for this entire lecture will be done with what's actually on the quiz and actually on the assignment in mind. You'll see that on the next slide. Finally, get those 15 points for the live classroom. I'll be giving out the passphrase towards the end of this lesson, so stay tuned for that. Okay, that's the overall summary. Now here is the topics that are covered, all of them. Should we know them? Yes. Are they emphasized either on the assignment, usually, or on the quiz? Generally, yes. So I will omit a few of these, but just talk about them in passing since they're covered in very small measure throughout the unit. But I will be covering in order the topics that are in red. Let's go ahead and get started. Limiting and excess reactants. These are useful when you're mixing random amounts of substances. Clearly, you'll run out of something first. Just like if you had 100 hamburgers but only 150 buns, something is going to run out first, right? In that case, I guess you had an excess of the buns. Same kind of thing. Here, we're burning 100 grams of butane, perhaps in this Bic lighter, and we happen to have exactly 100 grams of oxygen available. How many grams of carbon dioxide will we make? I'll show you a reliable method for doing it, and I'll also show you a shortcut method that you can give a try to. The tried and true method is to see how far each one will take you. How many grams of carbon dioxide can we make from 100 grams of butane until we run out? And similarly for oxygen. The lower number will be the one that is true because at that point you're out of that reactant. So this is a 3-step gram to gram conversion. So start with what you're given. Let's do butane first. Let's see how much CO2 it can make. So since you know it's a 3-step conversion, gram to gram, draw your 3 lines. You should also write equals blank grams of CO2. Then work your way from grams of butane to moles of butane. Happens to be 58 grams per mole. Moles of butane can make 4 times as many moles of carbon dioxide. Do you see that? And a mole of carbon dioxide, always top left to bottom right, so it cancels, happens to have a mass of 44 grams, 12 plus 32. We have enough butane to make 303 grams of carbon dioxide. How about oxygen? Well, we have 100 grams of that as well, so also write equals grams of CO2. I'll go a little faster this time. 32 grams is a mole, but every 13 moles of O2 only makes 2 moles of CO2. It's going down. I suspect this will be our limiting reactant. And a mole of CO2 is still 44 grams, so we run out of oxygen for this reaction. After we've made 85 grams of CO2, that's your answer. You could try it a fast way if you're feeling confident, and that would be just to do molar amounts. In other words, 2 times 58, or 116 grams, requires 13 times 32, or perhaps about 400 grams. Since we have 100 grams of each, we don't nearly have enough oxygen. That's our limiting reactant, so you could skip this entire mess in here and just not do it. Most students get nervous about that and they do the reliable method. That is limiting and excess reactants. The next topic is theoretical and actual yield. Using our model for butane again, let's figure out what the theoretical yield for a given reaction is. That's the maximum amount of product you could make if everything goes perfect, which it never does. And it's also, you can think of it as the perfect score on a test, 100 points, for example. The actual yield is what you got. Just like if you're 76 out of 100 on a test, you get a 76 for your test. The actual yield will typically be less than the theoretical amount. You can use this formula, however, I never do. I just think of it as a grade on a test. If you were 56 out of 84, I'll bet you'd know how to turn that into a grade. That's what actual yield is. Okay, so let's try one. You got 50 grams of butane and excess oxygen, so we'll figure out the three-step gram-to-gram conversion to see how much CO2 can be made. And if you actually got 25, let's see how you did. As before, that's a three-step gram-to-gram conversion. Start with what you're given, draw the three lines, and I definitely would also write equals blank grams of CO2. That's where we're going. And this is the third time we're doing it, so let's go a little faster. 58 grams is still a mole. You do get a four-fold increase, which is nice, and that CO2 weighs 44 grams. You've got enough to make, after we cancel everything out, 151.5 grams of CO2. That's disturbing because we only got 25. That's certainly an F on a test. We're 25 out of a possible 151. That's a 16.5% actual yield. This is theoretical and actual yield. The next topic is completely different. It's about energy and water. It's a fun question to consider. We need to know how much energy it takes to heat things up and cool them down. It's not as simple as you might imagine because there's phase changes involved. Ice is a great one to work with, which you're going to take 18 grams of cold ice, bring it up to its melting point at 0, bring it past it's all the way up to 100 as a liquid, and then go 10 grams further. This is a 5-step conversion. 3 for the temperature changes, 2 for the phase changes. So there it is shown graphically. 10 degrees to get it to its melting point, whole 100 degrees to get it to its boiling point, an additional 10 degrees to get it to 110. At 100 and at 0, it's going to take some energy to change the phases. So there it is, minus 20 degrees ice. And there's all 5 steps. For that first 20 degrees that we discussed, let's use Q equals mc delta T. We'll do that for any temperature change. After all, we know the mass is 18 grams. We know the specific heat is, be careful, it's not 4.184 because this happens to be ice. 2.03 joules per gram degree Celsius, and we're going 20 degrees. It takes 731 joules just to get it up to its melting point, at which point it will most certainly melt at 0 degrees. That takes 334 joules per gram, and we still have 18. We'll always have 18. Takes a similar amount, 6,000 joules in this case. Now it's time to bring up that cold water all the way up to from 0 to 100. So let's once again use Q equals mc delta T, 18 grams, 4.184 joules per grams degrees Celsius. Since it's a liquid and we're going the full 100 degrees, another 7,000 plus joules need to be added in. It's time to boil. This requires 2,260 joules per gram, a lot more energy. 18 grams once again, that's 40,000 joules. That's our big time player right there. A final 10 degrees to go from steam to hot steam. Q equals mc delta T there as well. Still 18 grams, 2.01 this time. See it? It's steam. 10 degrees is our delta T, giving us an additional 361 joules for a grand total of 55,000 joules. Let's relate that to nutritional calories to give us a feel for, say it's the same amount of energy as eating a ham sandwich, something like that. Well, There's 4,184 joules in a nutritional calorie. A joule is a tiny unit of energy. So this is only 14 nutritional calories, the same amount of energy you would get from eating a couple of potato chips. That is energy in water. Another question that is a little bit more challenging that you may see on the test in a similar but not identical form, hint, hint, is shown here. I like this question, but it's perhaps the most challenging question you'll see on the test. You got a chunk of ice and you put it into some room temperature water. At what temperature will it equilibrate? In other words, once all that ice is melted and it mixed, and assuming we have no loss of heat, what would be the resulting temperature? It's an interesting question. Now, we're not just mixing two things. If we were, and if they were the same thing, we could just take a weighted average, meaning this won't change it much. But this, after all, is ice. This water here that's at room temperature is going to melt it. So in my head, I'm saying, first, let's find out how much heat it takes to melt that ice. That will get consumed by this water, thus changing its temperature down a little bit. Once we've figured out what this temperature is, we then have water at 0 degrees Celsius a little bit, and water at something less than 23 degrees, a lot of it. We'll take a weighted average there because they'll simply mix and they're the exact same thing, and we'll find the new temperature. So how much heat is needed to melt the ice? That's not too bad. It takes 334 joules for each gram, and we have 4.52 grams. So that water is going to lose 1,507 joules as it melts that ice. Why don't we find out what temperature it will get to, right? Because we do need a final temperature. Rearranging for the change in temperature, we see that that's equal to Q, which is the heat. We figured that out, 1,507 joules. The mass of that water that is getting cooled down, that's the 55 grams, which has a specific heat of 4.184 joules per gram degree Celsius. Therefore, it will get 6.5 degrees colder, and since it started at 23, that brings it down to 16.5. That seems reasonable. What do we have in the container now? We've got some 0 degree water, a little bit, and some 16.5 degree water, which is cold, cool, a lot of it. So I don't think this is going to, if this is 90% here and this is less than 10%, I don't think it's going to cool it down much. To do a weighted average, first get the abundances of each. 4.5 of that 59.5 gram mixture, notice how I combine them, means we have 7.6%, which I have expressed here as a abundance. And the rest, now I think that 4 is a typo. This should simply be 55 divided by 59.5, or 92.4% of it, which I've expressed as an abundance. And note that they combine to equal 1, which is good. And then we simply do the weighted average. The abundance of one times its temperature plus the abundance of the second times its temperature will give us the resulting temperature. Now, I changed it to Kelvin, which some of you might miss. Now, in this case, maybe it's pretty clear because this is 0 Celsius. And anything times 0 is 0. So that would be weird, right? You'd be saying, wow, it doesn't matter what this is. No, it does. For any temperature calculation, you have to use Kelvin. So I added 273 to my Celsius, got my Kelvin answer, and then subtracted 273 to get back to my Celsius answer. And as predicted, it only went down another degree or so from the 16.5. And that is the answer to that problem. So our passphrase for this unit will be simply water. And I hope you heard that. Let's talk about solubility. Is that related? Well, in water, I guess it could be. And here are some aqueous solutions, right? Adding salts to water. Some are very soluble, nitrates, for example. Some are almost not soluble at all, like this sulfate here. There's table salt right in the middle. When you heat them up, notice the temperature is increasing. Nearly all of them get more soluble, right? The solubility increases. No surprise. Any cook could tell you that is true, right? But not all do. There's a couple weird salts that don't, so we can't say that's a law. If you only have a little bit of your salt in water, we could say that it is unsaturated. You could still add more of that solute, which is the dissolved material, and it will go right in. When you're exactly at the saturation point, that is the maximum amount of dissolved solute. Now, you might think you have to weigh it out very carefully to make a saturated solution of sodium chloride, but not true. Just add an excess. So imagine a glass of water with excess salt in it. You'd see the white powder at the bottom, and it would be true that any liquid above it would be, by definition, saturated. As much as possible came in. So if you just pour some of that out, you've got an exact saturated solution. Scientists love that. And if it's supersaturated, believe it or not, it can have more than it's supposed to be able to reasonably dissolve. That does happen sometimes. You take some sugar that's hot, you heat it up. As you cool it down, the solubility should decrease, but it stays in solution for a while. It remains supersaturated, not until you actually give it a chance, bump it or something. It might precipitate. That's a supersaturated solution. Let's solve two problems. We got 40 grams of salt per 100 grams of water. Based on this graph, how would you call that? Unsaturated, saturated, or supersaturated? Well, I made a point of giving it the point right there because look, 100 degrees Celsius, sodium chloride. How soluble is it? Looks like 40 grams for every 100 grams of water, which is exactly what they said. Therefore, it is saturated. How about for KCl at 25, which is right there? We find KCl, it's that dark blue line there. And they've added 50 grams. What's the deal? Looks like based on this graph, it can only handle 35. I would call that supersaturated. That's solubility. Mass percent and molarity are very important in all sorts of fields, including the healthcare industry, where you need to know what that saline solution is in terms of concentration. In the grocery store, you oftentimes see mass percent like a 7% vinegar solution. But molarity is what scientists like because the mole is a number, and that'll literally tell you how many particles of your solute are in that solution. So here's the formulas. For mass percent, it's just how much solute, like say salt, is in your solution. Turn it into a percent by multiplying it by 100. Now, circle that because everybody messes that up. That is not the solvent. That is the solvent plus the solute. So the solution means everything. And that is a very easy error to make. Same with molarity. In this case, we're going to quantify it in terms of particles. So we'll have the moles of that sodium chloride. For example, if we had 58.5 grams of sodium chloride, that would be a mole. And we'll divide that by the liters of solution. And don't forget that 1,000 milliliters equals a liter. If you got a number like 7 mole or something like that, that could indicate a fairly concentrated solution. So let's solve a couple problems. We got 100 mils of a solution, and it's also 100.5 grams, and it has 5.1 grams of sugar in the form of glucose in it. Let's get the mass percent. Well, there's our solution mass. There's our solute mass. Looks like 5.1 divided by 100.5. We've got a 5% solution by mass. Pretty dilute, I would say. What's the molarity of it? Well, 5.1 grams is what you have, but you need 180 grams for a mole. You only have 5/180ths of a mole, low number. Divide that by the liters of solution, and they only told you milliliters, but we need a whole 1,000 milliliters for a liter, so I think we have 0.1005 liters punched in. You get a 0.282 molar aqueous glucose solution. Now suppose we had to make a solution. We got to make a 1 molar solution and we need 100 mils of it. Well, if it was a whole liter, I'd just take a mole of this and dilute it up to a liter and I'd be done, 1 mole per liter. And that would be 40 grams. But I only need 100 mils and I don't want to make 1,000 then throw out 900. So instead of 40 grams, why don't I break it down tenfold since that's a tenth of a liter? Why don't I take 4 grams of sodium hydroxide and add enough water to make the volume of the solution 100 mils. Now, if you said add 96 mils of water, close enough for me, that would be fine. But the way I word it is probably the most exact way to do it. And there it is. We don't need a whole mole. We need a tenth of a mole. A tenth of a mole divided by a tenth of a liter is a tenth of a mole, is 1 mole per liter, 0.1 divided by 0.1. How are you going to do that? Go to the stockroom, grab sodium hydroxide, weigh out 4 grams, and then put it in something so that you can dilute it accurately to 100 mils using water. A narrow graduated cylinder might be a good tool for the job. Another random topic, acids and bases. I guess the theme is water here. And in this case, let's take a look at all these things and start by asking what they might be in terms of their acidity, acid or base. How about those oranges? Those are weakly acidic. They've got citric acid, for example. The lemons, sure, same thing. The lemonade, well, it's got sugar added, but that doesn't change the pH. It has neither H plus nor OH minus. The tea has tannic acids in it, for example. That's an acid. Milk of magnesia would help to know that that is magnesium hydroxide, and a hydroxide is a base. I'm going to say a base. Baking soda is a little tricky because it's sodium hydrogen carbonate. I don't see any OH minus in it. By the way, I'm recalling that acids contain H plus or make it in solution. Bases contain OH minus or make it in solution. Don't forget H plus plus OH minus makes water. So these require aqueous solutions. Baking soda does not have hydroxide, but bicarbonate does make it in solution. So that's a tricky one. That's basic. Batteries, you might quickly say, oh, alkaline, that means basic. But they could be acidic each as well if it happened to be a lead acid battery, which is not generally how these types are sold. Milk is hard to predict. It just seems slippery to me, but it's not. It checks in at just under 7, 7 being neutral. Below 7 for a pH means it's an acid. Above 7 means it's a base. More on that soon. Baking powder, that has a carbonate. Carbonate similarly can generate OH minus in solution, so that's a base. Vinegar is an acid because it has acetic acid. Tomatoes, just like almost any fruit, have some weak acids in there. Acidic as well. Oh, and if you add oil, it's worth considering. It's not an aqueous solution. There's no water present. It does not have a pH. Be careful not to say it's a pH of 0. That would be a strong acid. Okay, so in general, an acid has H plus or somehow increases the H plus concentration of a solution. Base, same deal with OH minus. Acids lower pH, bases raise pH. Neutral is 7. Let's make sure before we talk about where these exponents are coming from that you just know how to do a little exponent math. So just humor me. What is 10 to the minus 7th times 10 to the minus 7th? You should get 10 to the minus 14th. 10 to the 3rd times 10 to the minus 7th. I think you just add them together. So 10 to the minus 4th. 10 to the 10th. 10 to the minus 14th. And let's see what we can say. If the H plus concentration of one of these solutions is 10 to the minus 7th moles per liter, these square brackets means moles per liter, they always add up to 14, this exponent. If that was 8, this one would be 10 to the minus 6. But in this case, 10 to the minus 7th is a nice match. This looks neutral to me, right? At pH of 7. The pOH is also 7. That just literally means the power of hydroxide. pH means the power of the hydrogen cation. It is 10 to the minus 7th moles per liter, but when we apply the power to it, power of hydrogen, you just take the exponent, right? That's how we do it. Absolute value. 10 to the minus 3rd, that's a lot more of H plus, right? 4 orders of magnitude. So the OH minus must be 10 to the minus 11 because they add up to 14. pH, 3. A for acid. N for neutral. pOH is 11. More hydroxide than H plus. 10 to the minus 5th, maybe you could predict that the hydroxide is 10 to the minus 9th, much smaller. That would be an acid. Your pOH would be 5. No, pH is 5, so pOH is 9. Sorry about that. Now, if your hydrogen ion concentration is exceedingly low here at 10 to the minus 13th moles per liter, well, the OH is going to be so much higher, right? 12 orders of magnitude higher. 0.1 compared to, oh my God, there's a lot of zeros in front of that. The pH looks like it's going to be 13. That's a base because it's above 7. pOH will be 1. Now, you can summarize this with some formulas here. Be aware that there's only 1 or 2 questions that show up on the assignments in the quiz for all this knowledge here, but it's good to cover it anyhow. If you're in really deep trouble or you need to rush through, you could consider skipping this if you absolutely had to. But I'm going to do the whole thing. Based on what we talked about before, all these formulas spit out nicely, right? It's always true that if your hydrogen ion concentration is, say, 10 to the minus 7th, so will be your hydroxide concentrations. They always multiply through 10 to the minus 14th. Using this powers type formula, that means the exponent of each could be 7 and 7, 6 and 8, things like that. And we can figure out the hydrogen ion concentration if we have a pH by just taking that pH 10 to its negative power, and that would be its concentration. So if we had 10 to the minus 6, that would be its pH, right? 0.000001. Same thing for pOH. And how do we calculate the pH if we know the hydrogen ion concentration? Well, if it's 10 to the minus 6 molar, the pH is 6. And if you take the negative log of 10 to the minus 6, that's 10 caret button minus 6, you would get pH of 6. Same thing for pOH. Now, if that all made total sense to you, wonderful. You could probably skip all this stuff, but I want to show you where it all comes from. So let me work my way back a little here. Let's start from the ground up. Let's say you're not comfortable with logs and exponents. What is 10 to the second power? Maybe you're aware that that's 10 times 10, or 100. We could say that 2 is the log of 100. So log means the exponent number. 10 to the minus 2, that's less than 10 to the 2, less than 10 to the 1, less than 10 to the 0. So we use put it in the denominator, 1 over 100, which is 0.01. And there you go. We'd say negative 2 is the log of 0.01. So logarithms are the exponents. Let's solve a couple problems. If the hydrogen ion concentration is 10 to the minus 2 molar, that's way more than normal water would be at 10 to the minus 7th. Let's say that the pH is 2. So if you're into math, you should be able to deduce that pH is the negative log of the hydrogen ion concentration, and 10 to the minus pH is the hydrogen ion concentration. There actually are a couple questions on this. Just use these formulas, get your answers. Similarly, we can say the same thing for pOH. Good, and that's where 4 of those come in. Now, I'll give you a hydrogen ion concentration, you give me a pH. It's 0.0001 molar, or 10 to the minus 4th molar. pH, 4. It's 10 to the minus 1 molar, pH, 1. It's 10 to the minus 0.84 molar. Oh God, I don't know. That's like lower than 1, but I would do 10 caret button minus 8, no, I'm sorry, negative log of 0.84, and I'd get 7.5 times 10 to the minus 2. And if you had a 4 molar solution of a strong acid, that would be completely dissociated. Its H plus concentration would be 4 molar. So we need the negative log of 4, and you get a number below 0. Yes, pH for super strong acids can go below 0. Now I'll give you a pH, you give me a hydrogen ion concentration. pH is 7, H plus is 10 to the minus 7, 10 to the minus 3. 10 to the minus 3.4, which you could plug in and get a better answer for. So same thing with 10 minus 12.62. So going from one to the other is not too hard. Let's imagine that your pH is 3.78. What is your hydrogen ion concentration? Well, I do these, I just look up H plus equal, and nicely 10 to the minus pH, which is 3.78, is the hydrogen ion concentration. So if I type in 10 caret button 3 minus 3.78, I get 1.66 times 10 to the minus 4th. Now they add up to 14, see that? pH plus pOH, so this has got to be 10.22. I could do this a variety of methods, but I would probably just do 10 to the minus 10.22 equals, very low number, 6.0 times 10 to the minus 11. Is this solution acidic or basic? Well, if the pH is 3.78. You're well under 7. That's a weak acid, but it's an acid nonetheless. Examples could be some fruits and vegetables. Now let's talk about equilibrium. I think this is the second to last of our topics. This is an interesting thing. Sometimes when you mix things together, they don't go to completion, right? And the reason is that if you're doing a chemical reaction like the thousands that are occurring in your body right now, A plus B, for example, would turn into C plus D, but there's no reason all too often why D plus C can't go backwards and turn to A plus B. We call that chemical equilibrium. It's the state at which the forward rate equals the reverse rate. Avoid saying chemical reactions are stopped. Generally, they just hit a state of equilibrium. And scientists decided to measure it by taking the concentrations of C and D, where they used the coefficients for exponents, divided by the reactants, A and B. And once again, any numbers in front become exponents. So they're important. Now, in general, this equilibrium constant, if it's a very low number, means it's hard to get the reaction to go anywhere. And if it's a high number, well, it goes just fine on its own. In order to express this, don't include anything that's not in that cannot be in equilibrium. And if you have some like rock and water, the rock's not going to go back and forth. So we omit the things that are not in solution, the liquids and the solids. If it's all gases, that's fine. But think about each case whether it's part of a nice solution that can mix. This one is gas, gas, gas. So I'll put products over reactants. Coefficients like this too become exponents. And there you go. How about this one? It looks fine except, oh, look at a solid and a solid. We omit both of those. The equilibrium is just those two. And I'll bet it's very measurable. Here's another one where we're taking hydrogen sulfide and decomposing it. It's got a lousy equilibrium. And if, and by the way, you see this one here? This is beyond the scope a little bit for this course. They're going to have you actually plug into this equation here. We'll create the equation, then plug in. So I'm just going to go over it fast. Set it up. Don't forget coefficients become exponents. And plug it in. Solve for hydrogen, which might need some rearranging there. And you'll find out that's its concentration. I think this is our last topic, Le Chatelier's principle. He took a look at chemical reactions and how you can push that equilibrium towards your desired end, whether it be forward or backwards. Let's imagine we have a generic reaction of A plus a bunch of B's forming C. I think that D is supposed to just be an arrow. And it's an endothermic process. You got to heat it up. Suppose we made a change, like we added some A. What would that do? That would shift it to the right. Reason? If it were a fire, for example, adding wood should certainly shift the reaction to the right. Whether that's valid, I don't know, but that's the one I give. Le Chatelier always talked about relieving stress. I never really liked that. If you add product, that's C, it's going to go the wrong way. Quenching the flame. If you add heat to it, the rule is heat it if it needs it, and this is a positive value, meaning it needs heat to go, so that'll help. If you pressurize it, we have a weird rule. It'll always favor the fewer numbers of moles. Now remember there's an arrow there where that D is. But there's 4 moles of stuff on the left, 1 plus 3, and only 1 on the right. So pressurizing it should help. There you go. Okay, so here's another one, and I'll have you do a whole bunch of predicted changes. We've got some nitrogen monoxide and some oxygen. It's forming 2 equivalents of nitrogen dioxide, and it requires some energy. So you have to come up with add NO. Which direction will it go in? It's a product, so it'll shift it to the left. No, it's not a product. NO2 is a product. NO is a reactant. It'll shift it to the right. Sorry about that. NO2, there it is. That'll shift it to the left. Add some oxygen. Looks like a reactant to me. It's in the equilibrium. I think that's a good thing. Remove some NO. Well, you're removing a reactant, thus creating a gap. That'll get filled in by shifting it to the left. That's a quick way to think about it, don't you think? Remove NO2, it got a gap on the right. It needs to get filled in by shifting the reaction forward. Remove some NO2, I just did that. Remove some O2. That would be a gap right there. It wouldn't go. It would shift it to the left to make up for that. Increase the pressure. Favors the fewer number of moles. 3 turns into 2. That's good. It would go to the right. Increase the temperature. The rule for that, heat it if it needs it. This one happens to be endothermic, so that will help it. Decrease the pressure. Well, that would mean spread the molecules out, and it's the opposite of increasing the pressure. So if increasing the pressure went to the right, decreasing the pressure to the left. And big hint, you may see on the quiz that they choose to decrease the pressure by increasing the volume of a gaseous system. So imagine a small balloon, right, like this, and then we make it bigger, that balloon. It's going to spread the molecules out. It'll decrease the pressure, right? If you squeezed it in, it would increase it. Open it up, it decreases it. So therefore, in this case, it should go to the left. Okay, that is the review for week 5. Email me if you have any questions.